Hello everyone, welcome to the course PH3151 Engineering Physics. I am R. Swarnalakshmi, Assistant Professor, Department of Physics, Government College of Engineering, Chengipatti, Tanjavur. In today's lecture, we will be covering few topics in Unit 3 of the course PH3151 Engineering Physics. Unit 3 comprises of oscillations, optics and lasers. In today's lecture, I will be covering the concept of resonance. At the end of this lecture, a student will be able to differentiate between ideal oscillator and real oscillator, justify the need of forced oscillator, analyze the equation of motion of damped and forced oscillator and arrive at its solution, explain the concept of resonance. Consider an ideal simple harmonic oscillator. An ideal simple harmonic oscillator is a spring mass system oscillating on a smooth frictionless surface. When the surface is smooth and has zero friction, it means there are no losses. Since there are no losses, once the system is set into oscillation between A and minus A, the oscillations are sustained over long duration of time. That is, the system oscillates with constant amplitude irrespective of the time. The equation of motion of such a system is obtained by equating the inertial force to the spring restoring force. Inertial force is ma, the spring restoring force is kx. Both are directed opposite, hence the minus sign. From this, we obtain the equation of motion d square x by dt square plus omega naught square x equal to 0. Here omega naught is the natural frequency of the oscillator given by root of k by m. So the time period of oscillation, that is time taken for one complete oscillation, is time period t. It is given as t equal to 2 pi by omega naught. That is t is 2 pi root of m by k. The solution of the differential equation for an ideal harmonic oscillator is given by x equal to a cos omega naught t plus phi. Here omega naught is the natural frequency of the oscillator, phi is the initial phase, a is the amplitude, that is displacement from the maximum displacement from the mean position. Let us consider a real oscillator. A real oscillator is the same spring mass system. The only difference is that now friction plays a role. So there are losses due to friction and hence the equation of motion gets modified to the form ma equal to minus kx minus bv. The damping force is proportional to velocity. So this is the damping force. So this can be rewritten as d square x by dt square plus alpha dx by dt plus omega naught square x equal to 0. Here alpha is b by m. It is the damping constant and omega naught square is k by m, which is due to the spring restoring force. So we have the solution for this equation to be categorized into three categories. If alpha by 2 is very much less than omega naught, we get oscillatory solution. If alpha by 2 is equal to omega naught, it results in critical damping. Whereas if alpha by 2 is very much greater compared to omega naught, the system is said to be overdamped. So real oscillators fall under these three categories. Either systems exhibiting oscillatory solution, or critical damping, or overdamping. So a damped oscillator is one in which the condition for oscillation, or condition for oscillatory motion is met. So we have alpha by 2 is small compared to omega naught, which implies the oscillator will oscillate with a frequency omega prime given as omega naught square minus alpha square by 4, the whole root. The oscillation, the solution of the equation is given as x equal to a e power minus alpha by 2t cos omega prime t plus phi. The oscillation is slowly damped and the envelope of the amplitude is an exponential curve. So in a damped oscillator or in real systems, the damping plays a vital role and hence the amplitude decays with respect to time. Why do we need a forced harmonic oscillator? A driving force is used to make up for the losses. So the driving force compensates for losses. In all real systems, there are losses such as frictional loss, or air resistance. Whatever be the loss, the driving force tries to compensate for the losses. Hence, it can ensure sustained oscillation. It is a reliable source for oscillation and it overcomes losses. These three advantages forces us to make use of forced harmonic oscillator. In case of forced harmonic oscillator, we assume that the solution x equal to ap cos omega t minus gamma. This is obtained from the linear inhomogeneous second order differential equation d square x by dt square plus alpha dx by dt plus omega naught square x equal to f sin omega t, where small f is given as f naught by m, where f naught is the amplitude term of the driving force, f naught sin omega t. So, since the solution is of the form ap cos omega t minus gamma, after sufficiently long time, the time period of a forced oscillator t is given as 2 pi by omega, where omega is the driving frequency. Omega is driving frequency, that is the frequency of the driving force is known as driving frequency. The amplitude AP is dependent on F as well as omega. AP is given as F by root of omega naught square minus omega square the whole square plus alpha square omega square. So, if omega equal to omega naught, AP is maximum, which is evident from the graph. At omega equal to omega naught, the value of AP is maximum. AP is high if the damping term is small. AP is having low value if the damping is large. In the solution, x equal to AP cos omega t minus gamma. AP is the amplitude which is given by this expression. Gamma is the phase term which is given as tan inverse of omega square minus omega naught square by alpha omega. This explains the concept of resonance. That is, the system oscillates in resonance when the driving frequency matches the natural frequency. The driving frequency matches the natural frequency. The system is said to be in resonance. I hope a student will be able to differentiate between ideal oscillators and real oscillators, justify the need of forced oscillator, analyze the equation of motion of damped and forced oscillator and arrive at its solution, explain the concept of resonance. Thank you for your attention.